So far, we've only looked at using alkyl halides as substrates for the SN1, SN2, E1, or E2 reactions. Now, if we could expand our substrate scope so that an alcohol could serve as the starting material in place of an alkyl halide, this could be advantageous, especially in light of the fact that many alcohol starting materials come from more sustainable sources than do the alkyl halides. If we propose using alcohols as the starting materials for SN2 or E2 or the E1, SN1 pathways, and we think about the hydroxide being the leaving group instead of the chloride, bromide, or iodide that we saw in the alkyl halide examples, this is really not a good idea because the hydroxide that would come off as the leaving group is a strong base. We know that a strong base is an unstable anion relative to many other common anions. It's a poor leaving group. Now, the SN1 reaction requires a good leaving group. So does the E2 reaction. So do the E1 and SN1 reactions. So we can't just toss an alcohol in instead of an alkyl halide and think that we'll be able to get the same type of reactivity that we saw for alkyl halides. We'll need to adapt our reaction conditions in some way to activate that OH leaving group, make it into a good leaving group, and then possibly we will be able to use alcohols as starting materials for some of these routes. One of the simplest ways to change the OH into a good leaving group is to use a strong acid to protonate that OH group. A protonation is a coordination of some group to a proton. If we were to do that, we would be able to get formation of this initial species. This is called an Oxonium Intermediate. The Oxonium Intermediate now has changed the OH hydroxide that would be a bad leaving group into an H2O. If that was to leave in the heterolysis, that's the first part of the SN1 reaction, would come off as water, a very stable leaving group. That would leave the carbocation, which could then undergo coordination to form the final product. In this case, the final product is an alkyl halide. If we review the steps that we had to undertake to get the alcohol to undergo the SN1 reaction, we had to first activate the OH group to be a good leaving group, and that's going to be necessary whether we're doing an SN1, SN2, E1, or E2 pathway, so we'll keep that in mind. And then we do the usual SN1 pathway, which is a heterolysis followed by coordination. Everything else we learned about the SN1 reaction of alkyl halides will apply here, because once you've activated the alcohol to be the Oxonium Intermediate, everything else happens the same way. If we consider an SN2 pathway, we know that methyl primary and secondary alkyl halides work with an SN2 pathway. Really, for alcohols, methyl or primary will be the best substrates for SN2 reactions of alcohols. And if you take a look at the general pathway, you're going to have to first do a protonation so that you get a good leaving group instead of the hydroxide leaving group. So you have this Oxonium Intermediate, just like we saw for activation to be able to do an SN1 reaction on page 179. And now we do the SN2 reaction by exactly the same type of route that we would do if, instead of having water as a leaving group, we had a halide as a leaving group, and we get our product. So take a look at the steps, make the OH into a good leaving group, and then do a normal considered SN2 reaction. Everything else we've learned about the SN2 reaction still holds here. We would still have Walden inversion if our reaction took place at a chiral center, and the less sterically encumbered substrates react faster, etc. If we want to push our alcohol towards an elimination pathway, we will still need to first activate our leaving group so that we get this Oxonium Intermediate, so that water would be a good leaving group. If we don't want a nucleophile to attack the intermediate carbocation so formed, we need to have a counteranion for our strong acid that is very poorly nucleophilic. And this sulfonate counteranion is a good example of a non-nucleophilic counteranion because it has these three non-hydrogen branches, very poor nucleophile. In that case, once your water comes off, it may facilitate the electrophilic elimination of the proton adjacent to the carbocationic site. So if we just look at what happened after activation, heterolysis followed by electrophilic elimination, well, those two taken together are what we define as being an E1 reaction to yield this alkene product. Everything else we learned about the E1 reaction will hold here. You'll notice that you can't do this on a primary alcohol. You would need to generate a carbocation that's either secondary or tertiary in general. And all those things we learned about E1 reaction, looking for a carbocation rearrangement and all of that, will still hold. The most common reagents you'll see as acids to have non-nucleophilic anions are sulfuric acid and phosphoric acid. So look for those reagents reacting with alcohols to give E1 products. Now, protonation of the OH group with a strong acid is a great way to activate the OH group. Then it's an H2O group. Water is a great leaving group. There are some cases when you may not be able to or may not want to use a very strong acid in a reaction. So people have developed other ways to activate an OH leaving group. In the case of using PCl3 or PBr3, where in this case X equals chlorine or bromine, you can see that a very strong partial positive charge could be induced on the phosphorus by those 3 electronegative atoms around it. That will attract the lone pair from the oxygen atom as shown, and you'll be able to kick off one of these X groups as an X minus chloride or bromide. If you do that, you have this new species in box B, where this whole group is sitting right where the hydroxide used to be. And in the case of bromide, you'd have bromine in those 2 spots. Once you've activated that in that way, your third X minus group, the group that got pushed off in this step, that will serve as your nucleophile to do an SN2 reaction. So the PX3, whether it be phosphorus trichloride or phosphorus tribromide, will lead to activation of the leaving group, and then you'll get an SN2 reaction. And of course, SN2 reactions don't work on tertiary alcohols, but they do work on methyl primary and secondary. So we've seen a way to activate hydroxide to be a good leaving group with a strong acid. We've seen how we can react it with phosphorus trihalide. And we have a third way here that's very common using this reagent. This reagent is known as thionyl chloride. And the first step that occurs when thionyl chloride comes in contact with an alcohol is driven by the fact that there's a very strong partial positive charge on that sulfur because you have electronegative atoms, oxygen and 2 chlorines, all pulling electrons away from that sulfur. So there's a very strong pull of that sulfur as an electrophilic site for lone pairs. An alcohol has lone pairs to be pulled towards that sulfur. So if we do this process and push electrons towards the sulfur, one of the bonds to the sulfur has to break, so it doesn't have greater than an octet. And the pi bond breaks selectively. This is a nucleophilic addition when a nucleophile adds to a site, the sulfur in this case, with attendant breaking of a pi bond. And that leads to this species here. Now we can kind of think through, well, what would be the most spontaneous thing that this species in box A could do? Well, we see there's a negative charge on the oxygen. Chlorine is a larger atom than oxygen is. So if you were to do a nucleophilic elimination where the anion is now negative charge from chlorine instead of oxygen, we should expect that to be a spontaneous step. And that does in fact happen spontaneously. And now we have the species in box B. This particular unit is a really good leaving group. If we do an SN2 reaction on this site, we can push this group off. Now, once this group is pushed off, it's initially going to look like this, and that has a resonance stabilized anion, so that's a pretty good leaving group. Now, there are some other steps that happen to the inorganic parts, the sulfur and chlorine containing parts, but what we're most concerned with is the fact that we've done an SN2 reaction on the organic part where this nucleophile is attached to the carbon center from which the oxygen was released. So again, if we review the different steps we had to undertake, we activated the leaving group, and this involved 2 steps, nucleophilic addition, electrophilic elimination. It makes it more complicated than the other 2 cases we looked at so far. Once that's activated, however, to form the species in box B, we do a simple SN2 reaction where everything we learned about SN2 applies. It won't work on a tertiary site. If we did have a chiral site, we'd have Walden inversion. Now, the three routes we've considered so far for using alcohols to do substitution reactions, whether it be using a strong acid, whether it be using phosphorus trihalide or using thionyl chloride, all those routes eventually led to halide as the product. I'm going to show you one way to make the OH into a good leaving group where we can then stop the reaction and bottle this up separately and do a second step to replace the OH with things that are not halides. This will allow us to access a bunch of different products that we couldn't access otherwise. In order to do this, we're going to use a sulfonyl chloride. So the sulfonyl chloride starting material should not be confused with the thionyl chloride. So the thionyl chloride has 2 chlorines on the sulfur and only 4 bonds total. This was on the previous page. The compound we're using now is sulfonyl chloride, which has only 1 chlorine, and it has a total of 6 bonds to it because it has 2 oxygens. Now this sulfur again has a great deal of partial positive charge by merit of the polar bond to the oxygen and the chlorine. So we'd expect a great driving force to pull electrons towards that electrophilic site to do a nucleophilic addition, similar to what we saw with the thionyl chloride. And then once we get to the species in box A, we would again expect it to be spontaneous to push the chloride out. Now in the case of this reaction, we usually choose our solvent so we'd precipitate this out as a salt, so the chloride will not attack this other species. But we have accomplished placing this leaving group where the OH used to be to form the sulfonate esters. Sulfonate esters are very useful because this sulfonate group is a really outstanding leaving group. And we can explain that by drawing all the different resonance contributors this sulfonate ester has, where you can start off with the minus charge here and push it around to the other oxygens in the structure, like so to get this anion in box A, and then push that negative charge again down to the bottom oxygen. So this is a very resonance stabilized species. You have 3 different resonance contributors. Makes it very stable, which is a good leaving group. Once we've installed this really good leaving group, we can then take any nucleophile, dump it into the solution, and undertake an SN2 reaction. Now, 3 of these sulfonate leaving groups have specific names with which you'll have to be familiar because they're used so commonly by organic chemists. And they differ only in what this R group is, right? Regardless of which unit we're talking about, all the resonance contributors will be the same. We still have a good leaving group in all cases. But if the leaving group happens to have this unit as the R group, this is called a tosylate leaving group. And sometimes people abbreviate it simply as OTS. I've drawn it in the anionic form. If we just have a methyl group, that is called a mesylate, and sometimes people abbreviate the mesylate leaving group as an OMS, and triflate, which people sometimes abbreviate as OTF. These are the only 3 specific ones I'm going to ask you to know for our class. If you see those, you should think, well, that's an outstanding leaving group, and apply reactants you know from there. And that really is the end of the discussion on SN1, SN2, E1, and E2 reactions. In the beginning of our discussion, we talked all about how those reactions work on alkyl halides. And here in the last few slides, I've showed you how you can use an alcohol as long as you activate the OH first, either with a strong acid, with phosphorus trihalide, with thionyl chloride, or you can use a sulfonyl chloride. And now we're going to transition to seeing some other reactions that one can use alcohols as a starting material to carry out. And we're going to talk about oxidation of alcohols. To do that, I want to first give you an organic chemist's definition of oxidation and reduction. First of all, let's think about the simplest reaction of an organic compound with oxygen that we can think of. And this would be a reaction with oxygen, not with water. So we define oxidation perhaps as reaction with oxygen. And this is one of the first reactions we probably learned how to balance when we learned chemistry. When you have a combustion reaction, all of the hydrogens on the carbon are replaced by bonds to oxygen. Right, there are 4 bonds there if you draw out carbon dioxide. There are actually 2 double bonds to oxygens. One definition of oxidation that organic chemists use, and one that we'll discuss here, is replacing bonds between carbon and hydrogen, and instead replacing them with bonds to oxygen, and in some cases to other more electronegative atoms as well, more electronegative than carbon. But here we're going to focus just on the bonds to oxygen being formed. Now in the combustion reaction, we took a reaction of an organic compound with oxygen and replaced all 4 bonds with bonds to oxygen. We don't have to go all the way from methane to carbon dioxide in one step, however. There are bacteria that have enzymes that can take the methane from natural gas in the ground and make it into methanol. And they use that as an energy source to do other reactions and build other parts of their biological structures. If we take methanol, we can oxidize it again. So you see we've already replaced one of the bonds from carbon to hydrogen with a new carbon-oxygen bond. If we want to oxidize this by 1 more unit, we would need to have a species with 2 bonds to oxygen, and now we are down to only 2 bonds to hydrogen. And this is an aldehyde. We can oxidize this again, and now we have a total of 1, 2, 3 bonds to oxygen, and only 1 bond left to hydrogen. And a fully oxidized carbon atom will then, of course, have 4 bonds to oxygen. So with this definition of oxidation in mind, let's take a look at what kind of reactions we might be able to do with an alcohol starting material, kind of like what we had starting here. We're specifically going to try to make aldehydes and carboxylic acids by doing 1 or 2 units of oxidation on an alcohol starting material. Chemists have, in fact, been able to identify reagents that can facilitate replacing bonds from the alcohol carbon to hydrogen, replacing those with new carbon-oxygen bonds. The type of reagents we'll talk about in this portion of the class are all chromium-based reagents. Cr is the element chromium in the periodic table. And regardless of which combination of chromate anions with acid or dichromate anions with acid, or even chromic acid with an added acid like sulfuric acid, that specifically is called the Jones oxidation. Regardless of which of those types of conditions you see, you will have the ability to replace all of the hydrogens on the alcohol carbon with new bonds to oxygen. Right, here we have 2 hydrogens on the alcohol carbon. If we use one of these very strong oxidizing agents, it should replace both of these bonds to hydrogen with new bonds to oxygen. So we're not going to stop at just replacing one of the CH bonds. We're going to go and replace the 2 bonds that used to be to hydrogen with new bonds to oxygen. You'll always start by making a second bond to the oxygen that's already there and taking one of the hydrogens off. That would get you to this point. It's 1 unit of oxidation. But you don't stop there. The second step is going to be to remove that second hydrogen and add a new oxygen in its place. So the final product you would get would be the carboxylic acid. This is the only route we've seen in our course so far to be able to produce carboxylic acids. Now, what if I had a primary alcohol and I did not want to go all the way to the carboxylic acid? What if I wanted this intermediate species, the aldehyde? Well, people have discovered a way to make a less powerful oxidizing agent, PCC, that is an abbreviation for this structure here, pyridinium chlorochromate. PCC always mediates only 1 unit of oxidation. And those other ones, as I mentioned, mediate full oxidation of all available hydrogens on the carbon that has the OH on it. So if I want to stop after only 1 unit of oxidation where I take and replace only one of these hydrogens with a bond to oxygen, I would have to use PCC. If I took PCC and did this reaction, I would get the aldehyde, and it would stop there, leaving 1 hydrogen in place. Now, if I had a secondary alcohol, it only has one hydrogen to be replaced. So whether I use one of these strong oxidizing agents, like sodium dichromate with an acid, or if I use PCC, it doesn't matter. PCC can do 1 unit of oxidation, so make 1 new carbon-oxygen bond. The sodium dichromate with acid, it can do 2 units, but there's only 1 unit possible here. There's only 1 hydrogen attached to that carbon with the OH on it. So it's also going to produce this ketone. So this is really a very, very important set of reagents we can use, because it's the only way we've seen so far to make carboxylic acids, aldehydes, and ketones.